Time for us to do some problems that involve using the properties of the gradients. And so we're going to do some various things like linear approximation, finding tangent planes, even finding the gradient itself. So it's going to be a lot of fun stuff. Now this is a really important topic because the gradient is a wonderful stand-in for the derivative when we're in our multivariable setting. So it's important to get comfortable with it, which means practice. Practice as much as you can. If you're following along with the video, pause me whenever you see a problem and do it yourself first. This is how you develop intuition, how you start to really get that fun, ooh, this is a puzzle, and not that like, another one, because we want you to enjoy it. Math should be enjoyable. At least if it's done correctly, it should be. Well, let's begin. Our very first problem. Let f of x, y, z equal a half x squared y cubed z plus 5 halves z squared. Find a unit vector, all right, in the direction in which f increases most rapidly at the point -2, 1, -1, and find the rate of change of f in this direction. Now there's a couple of key things going on here. So we do see direction, and we're talking about things where we see like rate of change. Of course, rate of change is code word for derivative. So in some sense, this has something to do with directional derivative. But there's another key thing here. And so what's the other key? Well, it's this phrase, increases most rapidly. That's a really important phrase here because we're really trying to test. Do you remember what tells us about increasing most rapidly? And so here, the real challenge, the real problem here is saying, do we know what's being looked for? In our case, we say, aha, we've heard of things increasing most rapidly. Namely, if we look at the gradient of f at a particular point, we say, look, the magnitude of the gradient equals the rate of greatest increase. In other words, it's, if you want to go up as fast as possible, how fast can we go? Well, look at the magnitude. And the direction, it's the direction of greatest increase. So this is how to move to go up as fast as possible. In essence, what you can think of, it's almost like we're standing on a hill, right? So we have a hill, and here we can imagine ourselves standing on our hill. So there we are. And the question is, where do we move? So what the gradient tells us, the gradient says, hey, if you want to move fast, move that way. So the gradient is pointing the uphill, say that's the steepest way to go. Now if you wanted to move down, well, then you go opposite the gradient. But that's a different story. We want to move up. We're the optimist in this problem. Up, up, and away. All right, good. So this is really a question about the gradient. So let's start by looking at the gradient. What is our gradient? Well, we have the gradient of f is, now it's a 3-variable function, so we're going to have 3 slots. Take the derivative with respect to x first. Well, okay, the 2 comes down. So we're going to have x, y cubed, z. Well, there's no x there. When we take the derivative with respect to y, the 3 comes down. So we're going to have 3 halves x squared, y squared, z, again, that's as it is. And for our last one, derivative with respect to z. So 1/2 x squared y cubed, and here, derivative of 5 halves z squared with respect to z is 5z. All right, so the gradient of f at -2, 1, -1. Okay, so now we just have to be careful and pay attention to our signs. I think the hardest part about this problem, at least at this step right now, is whenever we have negatives involved, like, okay, make sure we're not losing anything. So let's be careful here. X is negative 2, y is 1, and z is negative 1. The nice thing about y being 1 basically says, okay, y being 1, we can pretty much ignore it. So we're going to have a negative 2 and a negative 1. Well, that makes a 2. Okay, that's not so bad. And it's positive, right, because we have two negatives multiplied together. Then we're going to have a negative 2 squared. So that's a 4, a 1, and a negative 1. Okay, so it's negative 4 times 3 halves. All right, well, negative 4 times 3 halves would be minus 6, comma. Okay, so we have 1 half, negative 2 squared. All right, that's 4. So that'll be 2 times 1. So that's 2. Then we're going to have 5 minus 1. Okay, 5 times minus 1 is minus 5. 2 minus 5 is negative 3. Okay, so there we go. 2, negative 6, 3. Now, what we need to do is really take that and pull it into its two parts, the magnitude and the direction. So here we go. Let's start with the magnitude first. So the magnitude of 2, negative 6, negative 3, well, that would be the square root of 2 squared, 4, negative 6 squared, 36, negative 3 squared, 9. 4 plus 36 plus 9, that makes the square root of 49, which is 7. All right, good. So now we're ready. In fact, the only thing left for us to do is write our answer down. So it says, find a unit vector u in the direction in which we're increasing most rapidly. The direction is from the gradient. So we say, okay, this is the right direction, but not a unit vector. All right, so we scale it. Scale it down, so we scale by a factor of 1/7. So our u, 1/7 of 2, negative 6, negative 3. And find the rate of change. So we can say, look, our rate of change, I'll just abbreviate ROC, that's the magnitude of it is 7. So we're done. We're done. This problem really tested us on, hey, do we understand gradients? And hopefully we do. And this thing is particularly saying, remember, gradients tell us about maximum rate of change. And so we said, okay, let's grab that and let's run with it. Well, good. A nice warm-up problem. It's always nice to have a nice, easy problem at the start so that we can sort of get the wheels moving, so to speak. Let's go to our next problem. The surface is xz to the fourth minus x cubed y squared plus 2yz equals 2, and 3x squared z minus yz cubed minus x squared y squared equals 1. Okay, so we have like a surface here, and there's another surface there. They both pass through the point 1, 1, 1. Well, 1, 1, 1 is a really easy point to work with, right? Because you can just check. If you plug in 1, you get 1 minus 1 plus 2. Yep, that equals 2. 3 minus 1 minus 1. Yep, that equals 1. Yep, it's true. They both pass through the point of 1, 1, 1. Now, it says, find the unique line in parametric form, which is tangent to both surfaces at the point 1, 1, 1. Now, what's going on here? Well, I'm going to try to do a little bit of hand waving here just to sort of build up our understanding of the problem. Or you could say, look, this is, calculus through modern interpretive dance. Okay, so what's happening? Well, what's happening is you have a surface and you have a point. Now, when we think about a tangent to a surface, we don't think of tangent lines, we think of tangent planes. So if you have a surface and you have this tangent plane, well, how do lines fit in? Okay, well, what we can do, let's sort of imagine that we had something here. So we have this crazy surface. It's, it tends to be curved somewhat. And we have our point on our surface. And what happens is, lo and behold, we can say, look, there's a tangent plane. Now, how do we go from tangent plane to tangent line? Well, it turns out if I have a tangent plane, I have infinitely many tangent lines. And where are they? Well, the answer is just take any line that's in that plane that goes through that point. And what's going to be true? Well, what's going to be true is it'll be touching, because it passes through that point, but it just barely it just, barely kisses that surface. So we say, okay. So what's the idea? Well, we know that the line we want will be in the tangent plane to the first surface, but it will also be in the tangent plane to the second surface. So we have our great aha. And here's our great aha. Our tangent line is going to correspond to the intersection, corresponds to the intersection of our tangent plane. Our tangent planes, plural. So we say, great. All we have to do now is figure out what's happening with our tangent planes, and in particular, find our intersections. Well, it's not so bad. Now, when we think of this, we actually have some hope, right? Well, what do we need? We already have the point on the line, so we just really need to focus on the direction. We say, okay, well, that tells us something. Really, it tells us the following. We think back to our geometrical intuition. We invested time to learn to think geometrically. We should get some return on that investment after all. So we should say, okay, well, the direction of our tangent line, which is really, that's the hard part about this problem, is finding the direction. It's going to be in both planes, because the tangent line is in both planes. And so, how does that help us? Well, if I have a line that's in my plane, the direction of that line is going to be, this is the important part, perpendicular to the normal. So, we say, aha, that really corresponds to saying that our tangent line direction is perpendicular to both normals. And now, I think we can start to see our plan coming together. We say, perfect. Well, what do? We need to find the normal vectors for our tangent planes. And now we have two normal vectors. They're both perpendicular to our tangent line. So what do we think? Well, the first thought that should cross our mind, the cross product. Cross the two vectors together. That gives us the direction of the line that we're after. Wonderful. We've got a plan. Okay, so step one. Let's find our normals. So the way we do it, we're actually in really nice shape, because what we have is we can think of it as we have our functions here. I'll write the first one down. X z to the fourth minus x cubed y squared plus 2yz equals 2. Well, I can think of this as f of x, y, z equals 2. So whenever I see, some crazy expression equals a number, that's good news, because we know how to find the normals in that situation. Namely, our normal to our tangent plane at 1, 1 will be the gradient at the point 1, 1, 1. So we compute the gradient. As a reminder, before we get too far, if there had been variables on both sides, we would move some of the variables across. So in our case, they were nice. They only had variables on one side, so we don't need to do any of that moving around stuff. So our gradient of f is, Well, take the derivative first with respect to x, z to the fourth, minus 3x squared y squared, nothing there, comma, derivative with respect to y, minus 2x cubed y plus 2z, comma, and derivative with respect to z, 4x z cubed, nothing there, and 2y. Now, plug in 1, 1, 1, and what do we see? Well, we're going to get 1 minus 3, that makes negative 2, minus 2 plus 2, oh, that's nice, 0. 4 plus 2, 6. All right, minus 2 and 0 and 6. Great, great, wonderful. Now, where to next? Well, do the same thing with g. So, I mean, it's a technique so nice. We're doing it twice, right? We have two planes. So, with g, similar setup, we have 3x squared z minus yz cubed minus x squared y squared equals 1. So, our normal, think of this here as g of x, y, z. So, we want our normal to be the gradient at the point 1, 1, 1. Okay, so what is the gradient? Well, again, term by term. Partial derivative, what do we get? 6xz, all right, and no x, minus 2xy squared, comma, and then the next one, derivative with respect to y, minus z cubed minus 2x squared y, comma, and then with respect to z, 3x squared and minus 3y z squared. So plug in 1, 1, 1 again, 6 minus 2, that makes 4, minus 1 minus 2, minus 3, 3 minus 3, 0. All right. So, good. There's a couple zeros in our problem. That's a nice sign. Now, we have to cross product. Okay. So, we're going to take our two vectors, minus 2, 0, 6, 4 minus 3, 0, and we'll do our cross product. Okay. So, I, j, k, doesn't matter which order we do it, minus 2, 0, 6, 4 minus 3, 0. Okay, so what would that give us? 0i, oh, that's nice. 24j, 6k, then subtract 0k, subtract negative 18i, so it's add 18i, and subtract 0j. So it looks like we have 18, 24, 6. Now we could pull out a factor of 6. If we do that, 3, 4, 1. Now let's check. So 3, 4, 1 is at perpendicular to minus 2, 0, 6 and 4 minus 3, 0. Well, minus 6, 0, positive 6. Good. That adds up to 0. 12 minus 12, 0. Yeah, that adds up to 0 as well. And remember, since we pulled out the 6, we don't actually need the 6. We just need a nice thing. So this is perfectly good as our direction. So we have our point. We now have our direction. So the last thing is to put all that together. And therefore, we can say our line, it looks like x equals, y equals, z equals. We use our point, 1, 1, 1. Now our direction, 3t, 4t, and t. And there we go. That's it. That's the line which will touch both the surfaces simultaneously at the point 1, 1, 1. This is a nice problem because we get to say, oh, we got to use our gradients to find our tangent planes. But we also got to do a little bit of, hey, we have our geometrical intuition. It's good stuff. We like geometry. Highly recommend it. All right, well, let's continue. So, on to our next problem. Let g of x, y, z be a differentiable function. And we have the following. The rate of the change from the point minus 3, 4, minus 2 towards the point minus 3, 7, minus 2 is 6. The rate of change from the point minus 3, 4, minus 2 towards the point minus 9, 4, 6 is 6. The rate of change from the point minus 3, 4, minus 2 towards the point 9, 7, 2 is 6. Aha! Now, I don't want you to get nervous like, oh my gosh, 6, 6, 6. Ah! And there's nothing weird going on. This is not a crazy, evil problem. It's actually a beautiful problem, because what are we going to do? We're going to use that information to determine the maximum possible rate of change at the point minus 3, 4, and minus 2. Now, it's kind of interesting, right? Because you're at this point, it says, well, if you go that way, it's rate of change is 6. If you go that way, it's 6. If you head off that way, also 6. You're like, well, look, all these directions give us 6, so it must be 6 is the answer for any direction, right? Right. No, of course it's not. We can actually convince ourselves pretty quickly, right? Because if we can go that way and our rate of change is 6, if we headed that direction, so in other words, we went backwards, it would be negative 6. So it's not that every direction is 6. All right. So how do we figure this out? And what does this have to do? What are some clues in this problem to figure out what's happening? Well, there's a big clue. And it's this phrase: maximum possible rate of change. That kind of gives away what we're looking for. Because when we see the phrase maximum possible rate of change, we say, aha, there's something which actually gives the maximum possible rate of change, and that's called the gradient. So this problem really is asking us to find the magnitude of the gradient of g at the point minus 3, 4, minus 2. That's what we're looking for. Okay. Well, it's good to know what we're looking for, but now we have to think about how do we find it. Well, we know we're after the gradient, but there's also some other stuff. You see, there's a rate of change, and towards means a direction. So there's directional derivatives being given here. And so we say, okay, so directional derivatives also relate to the gradient. So we're given sort of 3 pieces of information about the gradient. And we're like, whoa, wait a second. Our gradient actually will be a vector with 3 entries. In particular, we can think of our gradient of g, of negative 3, 4, negative 2, as being a vector. Well, we don't know what the entries are. Once we do, we can get our answer, but we can think of it as A, B, C. All right, so now we kind of have an idea. Let's go and look at these bullet points, because all of these are about directional derivatives. They all have the phrase rate of change. They all talk about towards something, so that's saying in a particular direction. So if we can just figure out, okay, let's figure out what the directions are, we'll be in good shape. So let's think about just the directions. So we're starting at minus 3, 4, minus 2. We're going to minus 3, 7, minus 2. So the direction, so just think about how do we change? Well, we didn't change at all. We went up by 3, and then we didn't change at all. So 0, 3, 0. Well, wait a second. That's not a unit vector. So the real vector that we're going to use is 0, 1, 0. That's the unit vector that points in that direction. Okay, all right. How about here? Let's see what happened. We went from minus 3 to minus 9. that went down by 6. 4 to 4, nothing happened. Minus 2 to positive 6, well, that says we went up by 8. Of course, same thing, right? The problem here, that's not a unit vector. It's way too big. But we can actually do this one. In fact, we can probably do it in our head. Let's try it. No, we'll say it out loud. Negative 6 squared is 36. 8 squared is 64. If we combine 36 plus 64, we get 100. Which means when we take the square root, we get 10. So this has length 10. So divide by 10. So we have negative 6/10, also known as negative 3/5, 0, and 8/10, also known as 4/5. So that's that vector. This last one. Okay, negative 3 up to 9. Well, that's a lot of change. That went up by 12. 4 to 7. Well, that's 3. Negative 2 to positive 2. That's 4. Well, that one maybe we can't do in our head. But we don't have to do everything in our head. It's allowed for us to write stuff down. So, well, we'll make some notes somewhere. Let's put some notes up here at the top. Okay, all right. 12 squared plus 3 squared plus 4 squared. It's 144 plus 9 plus 16. 144 plus 16, that's not so bad. That's 160 plus 9 makes 169. Now, wait a second. That's a familiar number. 169 is 13 squared. Ah, okay. Wow, they chose some nice directions. All our directions are pretty clean. So, well, scale by a factor of 13. So this is 12 over 13, 3 over 13, and 4 over 13. All right, that's our real direction. Now, what we can do is we say, look, we have, in theory, the gradient. We just don't know what it is. And we have our direction vectors, and we have the directional derivatives. So we can rewrite our 3 bullet points in the following way. As 0, 1, 0 dot ABC equals 6. Because gradient dot our directional vector is equal to our directional derivative. And then, let's actually pull the 1/5 out front just because it'll be a little bit easier to see what happens. 1/5 minus 304 dot ABC equals 6. And you might say, Steve, wait a second. I thought you put the gradient first. You're right. Usually you do, but with dot product it doesn't matter, so we're okay. And if we pull the 1/13 out, 1/13, 12, 3, 4 dot ABC equals 6. Okay, cool. Now, let's clean this up. So, if we do our dot product, we'll get 0a, 1b, 0c equals 6. So we say, aha, b equals 6. Fantastic. We're already a third of the way done to figuring out what our gradient vector is. Woohoo! All right, next one. Let's multiply that by 5. So what do we have? Minus 3a, 0b, 4c equals 30, right? Because the 5 went across. Okay, all right, that's fine. We'll do the 13 across. So let's see, 12a plus 3b plus 4c, okay, that's our dot product going on, equals 6 times 13, 78. All right, good. Well, 3 equations, 3 unknowns. But like we said, we already had one, and we can use that, right? Since b equals 6, this 3 times 6 is 18, and then we can subtract that off. So we say, okay, updating, we have minus 3a plus 4c equals 30, and then 12a plus 4c equals 60. Right, because 3 times 6 is 18, and subtract 18 across. All right, good. Now, 2 equations, 2 unknowns. Our favorite thing. We love 2 equations and 2 unknowns. And so, for instance, if you multiply the first equation, say by a minus, and add to the second equation, because you see the 4c's, they're just perfectly set up for us to actually get some nice cancellation. Minus minus makes a plus, so we'll get 15 times a, cancellation there. 30 times minus, that's minus 30 plus 60. So that ends up with 30. We say, aha, that tells us a has to equal 2. All right, great. Well, now we know what a is. A has to equal 2. Well, that's just one thing left to figure out, and that's what is c. So for that, well, we just plug in, right? We know a equals 2. So, for instance, plug into our bottom equation. We now know 24 plus 4c equals 60. Okay, that tells us that 4c is equal to 60 subtract 24, 36, which tells us c is 9. Whoop. C is 9. Okay. All right. Good. Now, let's pause. We've done a lot of work. So we said, okay, we're after our gradient, because that tells us our max rate of change. We used our bullet points to say, oh, since these are directional derivatives, they're giving us information about the gradient. And we used the 3 bullet points, set up 3 equations, and solved for the entries. So what we've now done is we've figured out our gradient. In particular, our gradient of ABC is 9. Whoops, got in the wrong order. A is 2, sorry. B is 6, and C is 9. There we go. 2, 6, 9. That's our gradient. It's not our answer, but how do we finish? Well, we take the magnitude of that. So, whatever the magnitude of this vector is, that's our answer. So it's going to be the square root of 2 squared, 4, 6 squared, 36, 9 squared, 81. Well, 4 plus 36, that's 40. Add that to 81, gets you up to square root of 121. And that's another nice number. So we end up with 11. And that's the final answer. So we have, lo and behold, in these 3 directions, our rate of change is 6. We say, look, there's some other direction. The maximum rate of change by going to the gradient is 11. I really love this problem because it's so clean and it works out so nicely. It's one of my favorite problems. Okay, good. Well, farewell, problem. We're going to miss you. Don't worry. We'll still have some good problems left to come. We're not going to leave ourselves without fun problems. That'd be sad. All right, on to our next one. It's kind of similar. Given that our function is differentiable at our point 132, we're going to find the gradient using some information. All right, so what do we have? Well, we have a directional derivative at our point. In the direction of another point is 0. Okay, we have a directional derivative at the point 132, and the direction of the point 410 is also 0. So it's like, okay, so we know in that direction, our rate of change is 0. In that direction, our rate of change is 0. The directional derivative of g of x, y, z at the point 132 in the direction of the point 615 is positive. Okay, that's not really giving a lot of information, is it? All right, well, it is what it is. And we're told the magnitude of our gradient. The magnitude is 22. That's actually a lot of information. Now, in some sense, The least useful it would appear at the beginning is this part. Because all we're told is it's positive. It's not giving away much. It's keeping it, so to speak, as they might say in poker, keeping it close to the vest. So it's like, how do we use the fact that it's positive? Well, we'll figure that out once we get closer to it. But certainly we see there's a lot of gradient things going on. So let's start by looking at these first three bullet points, which are all about directional derivatives. And we want to take a closer look at them and see what they're telling us. So, for example, we're going from the point 132 in the direction of the point 442. Well, what's that direction? We went up by 3, right? 1 to 4, up by 3. 3 to 4 says up by 1, and 2 to 2 says by 0. All right, so that's our direction, 3, 1, 0. Well, it's the right direction. It's not the unit vector. Okay, but it's not hard to make this into a unit vector. Just find the magnitude, right? Square each entry, 9 plus 1 and 0. Add them up, gets 10. And so the magnitude is the square root of that. So 1 over square root of 10, 3, 1, 0. All right. So similar, let's do it here. All right, 1, 3, 2 towards 4, 1, 0. Well, up by 3. And then down by 2. And down by 2. Okay, well, same thing. It's not a unit vector. And we know it's not a unit vector because even as we look at the first entry, like that's changing by 3. That's way too much. Okay, pull it back, pull it back. What do we have? Well, do the same process, right? 9 and 4 and 4, if we add all together, makes 17. So 1 over the square root of 17, 3 minus 2 minus 2. And here, okay, was 5, up by 5, down by 2, and up by 3. And again, last time, find the magnitude. 25 plus 4 plus 9 makes 38. So 1 over the square root of 38 times 5 minus 2, 3. All right, there we go. So let's start with the first couple bullet points. Now, we're looking for our gradient. We know it's going to have 3 entries. The reason we know it's going to have 3 entries is it's a 3-dimensional problem, g of x, y, z. So we're going to say, let's let our gradient that we're trying to find look like something of the form of a, b, c. All right, so that's our gradient that we're trying to find. Now we're going to translate some of these pieces of information. The first bullet point says what? Well, if we take a, b, c, our gradient, dot 1 over root 10, 3, 1, 0, that's going to be equal to 0, because we're taking the directional derivative at our point in this direction is 0. Okay, now notice you can multiply both sides by the root 10, so you can get rid of the square root really quickly. Nice thing about 0 is it's a great way to get rid of constants. So this really is telling us that 3a plus b equals 0. Or if we wanted to, we could say, look, b is minus 3a. Well, that's good. We can actually say, look, instead of having to find a, b, and c, now we just have to find a and c, because once we have those, we get b as a freebie. Okay, let's go back. Part 2, bullet point 2. Again, translation, a, b, c, dot 1 over square root of 17, 3 minus 2 equals 0, because our directional derivative at the point 1, 3, 2, which is found by taking the gradient, dot this direction, because I want to go towards the point 4, 1, 0, is 0. So that's where the equal 0 comes from. So again, you can multiply, get rid of the square root of 17. Woohoo! Haha, good. It's nice not to have to deal with that square root. That was not a pleasant square root. And what do we get? Well, we get 3a minus 2b minus 2c equals 0, right? Because it's 3a minus 2b minus 2c. But wait a second. We actually know things, right? We have some relationships. See, for example, 3a plus b equals 0. So that says, hey, this thing right here, this 3a, it's really the same as b, sorry, negative b, right? Because 3a equals minus b. So we could say, oh, this says minus 3b is equal, or minus 3b minus 2c equals 0. Or what can that say? Well, if I add 2c and divide by 2, c equals minus 3 halves times b. Of course, b is minus 3a. So that would say this is the same as 9 halves times a. All right. So this is actually good. What we've come to is the following. We say we almost have our gradient. Using our first two pieces of information, we've gone from 3 unknowns to 1 unknown. In fact, that's usually what happens is every time you use a piece of information, you knock out a little bit of what's unknown. So since we've used 2 facts, it's not surprising we've been able to knock it down to just one thing left to figure out. In particular, this says, look, we can write our vector in the form, it's some number a, comma, then b is minus 3a, comma, and then c is 9 halves times a. The only thing left for us to do is figure out a. Well, what haven't we done? Like I said, the positive is kind of hard to work with. We'll come back to that in a second. Let's go to the magnitude. All right, so given that this is our magnitude, what can we come to our conclusion about? Okay, we can say our magnitude of a minus 3a 9 halves a, well, that would be the square root of a squared plus 9a squared plus 81/4 a squared. All right, great. So if we combine, well, okay, so let's make this all over 4, right? Everything has an a squared, so I'm going to pull it out. I'm going to put everything over 4. So I'd have 4 over 4 and 36 over 4, so that's 4 plus 36 makes 40, and 81 over 4 makes 121 over 4. Or, if you like, taking the square root of 121 over 4 is 11 over 2. Square root of a squared is... careful. I know you wanted to say a. It's actually absolute value of a. So we have to be careful. And now that all equals 22. Well, that's perfect. That tells us something. It says, hey, check it out. Absolute value of a divided by 11 multiplied by 2 has to be 4. Okay, now we're almost there. So our conclusion is we're down to really 2 possibilities, 4 or negative 4. So what is that telling us? It's telling us that if we come back to our gradient, well, it could be if a equals 4, that would be 4 minus 12, and then 4 times 9 halves, 18. If it was negative 4, well, it would be negative 4, positive 12, negative 18. So we've got a 50-50 chance. well, we're going to improve our odds. We want it to go from 50-50 to 100, right? We don't want to leave anything to chance. So now let's go back to our last bullet point. It said it's positive. We're like, what does that mean? Well, really, we say now we just have to ask, what happens when we take the dot product with one of these two vectors? So let's take it with the -4 case first, right? So if I take the dot product with this vector and that unit vector, would I have a positive or a negative? Well, a -20, -24, -54, yeah, they're all negative. So if I were to use this vector, I'd end up with a negative directional derivative in that point. Whereas if I use this vector, +20, +24, +54, everything's positive. And therefore, that is going to give me a positive directional derivative, which is what we need. So we know that this one is the answer. All right, good. So let's, that was kind of crowded down there. I'm going to rewrite it up here, but not do anything else. That's our answer. So this is the gradient of g at 1, 3, 2 is equal to 4, -12, 18. What a fun problem. Again, it's just sort of saying, let's piece together our information and figure out what can we get when we get to the end. All right, good. Well, let's keep going. More problems to do, right? There's always more problems. So our next problem. Given f of xy is sine of 3x plus 4y plus x times y minus x squared plus 6y plus 15. All right. Use linear approximation to f of xy at the point -4, 3 to estimate f of -3.98, 3.03. Now, we see the word linear approximation. If you're not comfortable with that phrase, just mentally say, okay, this really is just another way of saying tangent. In our case, tangent plane. All right, so what are we really doing here? Well, it's really about finding the tangent plane. Because the idea is that the function behaves like the tangent plane. And in particular, we have the following. We can say that our function, f of xy, is approximately fab plus f sub x ab times x minus a plus f sub y at ab times y minus b. And what this is saying, and again, we keep saying it over and over again, probably because it's an important idea. If you hear, math teachers keep repeating themselves, they're either trying to remember something or they're like, ooh, this is really, really important. And so we should spend some time repeating it so that it becomes set in stone. And this is one of the latter ones. So this is just saying this approximation is good near our point of tangency, so near AB. So our tangent plane looks like our function nearby, where we take it. All right, well, that's not so bad. Indeed, in fact, in essence, we just have to find the tangent plane, plug in the points, and we'll be done. So let's do it. All right, so first off, we'll do some work on the side here. Write down our function again. It's kind of a bit long, but that's okay. Sine 3x plus 4y plus xy minus x squared plus 6y plus 15. Derivative with respect to x. Okay, derivative of sine is cosine. Then we do the chain rule. Derivative of 3x plus 4y with respect to x will be 3. So that's 3 cosine 3x plus 4y. Derivative of x times y with respect to x, y Derivative of minus x squared will be minus 2x, and the rest is 0. Fy, xy. Okay, so again, go to the original function. Take derivative now with respect to y. Derivative of sine is, again, cosine. Chain rule now, taking derivative with respect to y. So it'll be 4 cosine 3x plus 4y. Derivative of x times y with respect to y is x. Derivative of x squared goes away. Derivative of 6y is 6. And the 15 goes away. Okay, so those are our partial derivatives. Now we need to evaluate. So we have our point here, we're told, negative 4, 3. So the function at negative 4, 3 is, well, negative 12 plus 12 is 0. Well, that's a nice number. Sine of 0 is 0. So that goes away. So 0, negative 4 times 3, minus 12, minus negative 4 squared. So minus 16. So remember, when you square a negative, it's positive. So we're subtracting 16. Plus 6 times 3. All right, that's 18. Plus 15. All right, some big numbers here, but not so bad. Minus 28 plus 33 leaves us with 5. Okay, that's respectable. F sub x at negative 4, 3. Well, again, we're going to get negative 12 plus 12 is 0. Cosine of 0 is 1. So a 3 plus y is another 3 minus 2 times minus 4. So that'll actually be a plus 8. Okay, 3 and 3 and 8 together add up to 14. And our last one, Fy at negative 4, 3. Okay, that'll be, again, cosine of 0 times 4. All right, 4 plus x. Okay, well, x is negative 4. So minus 4 plus 6. Plus 6. All right, well, there we go. There we go. Okay, equals, I should say, is 6. So we say, all right, this first term, 5. This next term, 14. And this last term, 6. Okay. So, cleaning this up, we have now the following. Okay, so it's approximately 5 plus 14, x minus minus 4, so x plus 4, plus 6, y minus 3. All right. Now, don't expand here. In fact, if we expanded here, it would make things tougher. We don't want that. We don't want things to be tougher. We want things to be better. So what do we do? Well, now plug in negative 3.98, comma 3.03. That's approximately, and notice, negative 3.98 and 3.03 is fairly close to our point. So that's why it's probably a good approximation. So 5 plus 14, negative 3.98 plus 4 plus 6 times 3.03 minus 3. So that's 5 plus 14 minus 3.98 plus 4 would get us to 0.02. 3.03 minus 3 is 0.03. So we have 5 plus 0.28 plus 0.18. Okay, if you had 0.28 plus 0.18, that's 0.46. And so we say, based on our tangent plane, our linear approximation, our function is approximately 5.46. It won't be exactly 5.46. There's definitely some error, but we weren't claiming it would be exact. We're just saying, look, the tangent plane is a reasonable approximation to what's happening to the surface. All right, well, good. Let's try another problem. All right, I think we have time for one more. One problem to finish us up. So, you have somehow found yourself in the middle of a desert island and need to estimate g of 0.97, 2.01, 3.02, where g of x, y, z is z of e to the power 2x minus y plus sine of xe minus 3. And for some reason, the only two you have available are coconuts. That doesn't sound so bad. Use linear approximation to give an estimate for the value g of 0.97, 2.01, 3.02. Now, if it feels like the kind of thing we talked about in the previous problem, it's because it's the kind of thing we talked about in the previous problem. In fact, what's the difference? Well, I mean, different function, different point, but the big difference is function of 3 variables. Do we change our approach? The answer is no, we don't. It's the same approach. So, what is the linear approximation to a function of 3 variables? It is the following. So g of x, y, z is approximately the function at the point we're interested in, a, b, c, c, plus g sub x at the point a, b, c times x minus a, g sub y at a, b, c times y minus b, and g sub z at a, b, c times z minus c. Now you might say, that's not a plane, is it? Well, it's not a plane, but you have to think about where we're at. When we have a function with 3 inputs and an output, that really puts it out into 4-dimensional space. So it's sort of like, what does 4-dimensional space look like? That's a wonderful question. I don't know. It's like 3 dimensions, but one more, right? And so what you have is not necessarily what you might call a plane, you might call it a hyperplane. And so if you ever hear anybody throwing around the word hyperplane, it really just means, something that's the higher dimensional equivalent. So like a hypercube. Sometimes you hear people talk about that. It's like, well, what's a higher dimensional version of the cube? All right, so we have sort of our more or less a basic same approach. We're like, okay, we need to find the function and all the partial derivatives, evaluate at our point A, B, C, and plug in. Now, there is one other thing that hasn't been explicitly said. What is A, B, C? See, that's a good question. So how do we go about figuring out? Well, oftentimes it gives us the problem in context. Otherwise, they might say, well, we have to figure it out. We're in the figure it out kind of problem. So what we do is we look at our problem and we say, okay, we're trying to estimate 0.97, 2.01, 3.02. And we say to ourselves, those sound like not fun numbers to work with, given that we have exponential functions and sine functions. But are there numbers nearby? Because remember, the approximation, this is good when we're near. So what we want to make sure is that we pick some points which are near and which we can say, those are numbers we're happy to work with. And I think we can see some numbers here. 0.97, 2.01, 3.02 says, okay, let's pick our choice for A, B, C to be 1, 2, 3. Those are nice numbers to work with. All right, other than taking a bunch of derivatives and evaluation, everything else is going to proceed more or less as we've done before. And it's just a matter of being patient. That's one of our strengths, right? We're patient people. It's why we became mathematicians. All right, g of x, y, z equals z e to the power 2x minus y plus sine of xz minus 3. G sub x Okay, that'll be, take the derivative with respect to x. There's an x here. The 2 will come down. So it'll be 2 times z, e to the 2x minus y. Here there's an x here, so you take the derivative chain rule. There'll be a sign, goes to cosine, and multiply by z. So plus z cosine xz minus 3. G sub y of xyz. All right, there's a y here. And when we take the derivative, it's going to come down minus 1. So minus z e to the 2x minus y. And that's it. There's only the one y. G sub z, well, there's a couple of z's. But they're pretty straightforward. There's a z here. And so that's just z times a constant from when we take the derivative with respect to z. So e to the power 2x minus y. Again, a chain rule. When we take the derivative with respect to z, there will be an x. So plus x cosine xz minus 3. Good. Well, plug stuff in. So what do we have? We're going to plug in 1, 2, 3. So g of 1, 2, 3 is, we're going to get, let's focus on these pieces because they're going to show up a couple of times. 2 times 1 minus 2 equals 0. 1 times 3, that's x times z, minus 3 equals 0. Okay, e to the 0 is 1, sine of 0 is 0. So we're going to be left with z, which is 3. G sub x of xyz, well, that's 2 times 3 times e to the 0, which is 1, so 6. Then 3 times cosine of 0, which is 3, which gets us to 9. G, whoops, not xyz, 1, 2, 3. I'm sorry. There we go, 1, 2, 3. All right, g sub y of 1, 2, 3. Okay, e to the 0 times minus 3, so that's minus 3. And g sub z of 1, 2, 3, e to the 0, 1, plus x, which is 1, times cosine 0. So 1 plus 1, 2. So we are going to put these together. We're going to get a 3 here, and we're going to get a 9, a minus 3, and a plus 2. All right, so let's update. What do we have? So we have our function. It's approximately 3 plus 9 times x minus 1, because a is 1, minus 3 times y minus 2, b is 2, and then plus 2 times z minus 3. All right. Great. We're almost done. The last thing for us to do is now plug in where we're trying to get our approximation, clean it up, and life is good. So g of 0.97, 2.01, 3.02 is going to be approximately 3 plus 9 times 0.97 subtract 1 minus 3, 2.01 subtract 2 plus 2 times 3.02 subtract 3. Okay, 0.97 subtract 1, well, that would be minus 0.03. 0.01 minus 2 is 0.01, so minus 3 times 0.01. 0.02 subtract 3 is 0.02, so plus 2 times 0.02. All right, well, that is 3 minus 0.27 minus 0.03 plus 0.04. All right, well, we're almost there. So what are we doing here? Well, if you 0.27, 0.03, it's really like subtract 0.3. but then add 0.04 back, so it's like subtract 0.26. All right, so that would make that, take 3, subtract 0.26, would be 2.74. All right, and there's our approximation. And you're probably thinking, we didn't use any of our coconuts. We just did it all by hand in linear approximation. Well, maybe we took a drink, got some nice refreshing coconut water. I hear it's full of electrolytes. All right, good. But the nice thing is, this notion of linear approximation just says, hey, tangent planes are wonderful tools. Tangent hyperplanes are wonderful tools. And in general, if we want to understand our function, if we know it really well nearby, we can use information about the point we know really well to get an estimate for the point we're trying to understand. All right, well, that's it for this session. I hope you keep practicing, because the more you practice, the better you're going to become, and I hope you come back. All right.